Our lecture today is based on the interval estimation for the two sample cases. We will also have a look at the hypothesis testing as well. So to start with, before we start discussing on the two sample cases, I would just make a quick recap of what we did last time on the one sample case. Now, here, we remember last time that we had a parameter, and the parameter that we were using was we had different parameters that we can estimate, but we focused mainly on the parameter mu, that is the population mean. We explained that we could make an estimation through the point estimation. We could also do an estimation through what we call interval estimation. All right, that's another possibility. And the interval estimation is what we are going to discuss now, is what we refer to as a confidence interval. And we studied what a confidence interval is about, and we learned that estimating the mean mu can be based on the point estimate plus or minus a critical value times the standard error. And the critical value is based on a certain distribution, and that distribution is a distribution of your statistic that you use there. And the statistic, if it is x bar, you will need to know what is the distribution of x bar. So we learned that in the large sample cases, the distribution of x bar is a normal distribution. Now, however, you will see, so as you note, the critical value is based on either the normal distribution, but it can also be based on another distribution that we refer to as the t distribution. Now, the t distribution, remember, is applied when your population standard deviation or population variance is unknown. All right, when your population standard deviation is unknown, this is where you apply the t distribution, and we mainly applied it for sigma unknown and n small, that is the sample size small. We did not apply it for the large sample cases for the different even if sigma was unknown, we did not apply it when n was large for the different reasons that I explained to you. One of it is that the t distribution approximates to a normal distribution when the sample size is large, and the other reason is for practical reason as well that I explained to you as well. So for practical reason in terms of finding the critical value from the appropriate distribution. So that's a little bit a very brief and quick recap of what we have been explaining last week. Now we are going to move on to the two sample cases. What's the difference? Normally for the two sample cases, we will observe that we are going to make use of this statement again to compute our confidence interval. That is the point estimate plus the critical value times the standard error. Things does not change. It's going to be the same everywhere. For each confidence interval that you're going to compute is the same idea. You have to have the point estimate plus or minus the critical value times the standard error. So what's going to happen? What's going to be the difference between what we did earlier and what we are doing now? So let me just erase this and then we discuss. Oops. So here last time we were estimating only one parameter mu. All right, we did an estimate based on one parameter mu only. But today we are going to change a little bit. That is, we will have two parameters that we will consider. We will have two parameters that we are going to consider. And what are these two parameters? What is the purpose of estimating two parameters? Now we're going to estimate two parameters. In what context shall we do so? This is what I'm going to explain now. Let me just take an example. Let's suppose I'm just going to take an example where let us assume you are an actuary. You're an actuary and you have a feeling you have a feeling that the premium or the claim amount, or rather the premium charged, or the let's change it like that. You have a feeling that the claim amount uh, that is made on a certain policy is different uh, for different genders, right? You believe that, for example, the claim amount for a certain health insurance policy rather, for male and that of female, you believe that they are not equal. You believe they are not the same. You believe that there is a kind of difference between these two measures. These two measures means the average claim amount for male and the average claim amount for female, all right, for health insurance policy. Now, one of the questions that you need to ask yourself now is whether this is true or not. Okay, and this is what we want to do today. We want to know if this is true or not by just checking it in a different way. Is that if you say that you believe that these are not equal, you are going to say, okay, mu m minus mu f is not equal to 0. That's another way of looking at the same issue. Mu m and minus mu f is not equal to 0. If it is not equal to 0, then it implies that there is indeed a difference in the average pocket money of male and the average pocket money of female. Now, if it is equal to 0, it means that there is no significant difference between the average pocket money of male and the average pocket money of female. So what do we want to do then? Look at before what we did. We wanted to estimate only one mean, but now what are we trying to do? We want to estimate that a difference. If we estimate that difference and we get a confidence interval that encloses 0, that would imply that there is no significant difference in the average claim amount of male and female. However, if the confidence interval does not enclose 0, then it means that there is a significant difference in the average claim amount of male and female. Now, how are we going to proceed then? So it's the same kind of idea that we did last time. So what we want to do is, if you want to estimate the average mu m minus mu f, let's suppose, you want to estimate what this is about, the first step would be to find your point estimate. And obviously, just like we did for mu, I'll just write the mu here. What we did for mu was we took the point estimate x bar plus or minus something. So for the case of mean, mu m minus mu f, you are dealing with two sample cases now, as you have observed. This is what we are doing here, dealing with two sample cases. So now things are going to change a little bit. Our point estimate will not be that same point estimate, only one mean, which estimate one mu. We'll have two different means that are going to be used to estimate these two different populations. There is one which is a population for male and one population mean for female. So what do we do then? The point estimate becomes naturally the sample average for male minus the sample mean for female. So that's the first step, is that we get the point estimate done. But the next step is what? Is to add or subtract a certain critical value. Now, I leave this open right now because just like we did last time, we explained clearly that there are two possibilities. Either you use the t-distribution, or you use the normal distribution, or you use the t-distribution. So this is why I leave it open. I'm not going to write anything here, z or t, because it depends on this, all right? What does it mean by depends on this? We'll get to that in a moment. And then times the standard error. Now, when we refer to the standard error, what would the standard error be like in here? Again, I'll leave this open for the time being. Why I leave it open? Because um, it depends on what kind of confidence interval you are applying. It depends on the condition. Conditions mean, are you dealing with small sample cases? All right, small sample size, small sample size for both small samples size. You have two samples here, small sample size, or are you dealing with large sample size, or are you dealing with the population variance being known or unknown? So it depends on all these different things, and you will see that it's not going to be so straightforward. So let's take the first case to illustrate this. If your We take a simple case if both sample size are large, that is NM and NF are large. Remember that when we did it for one population mean, we said one sample is large, but here we have two samples. If both are large, that is, if N is greater than or equal to 30 and N is greater than or equal to 30, that's already one condition. What's going to happen then? The other condition is that whether sigma is a known or known or whatever it is. But these things normally, as you would note, is that if sigma is known, well off, we are going to use a normal. Even if sigma is unknown, as we studied earlier, we're still going to be using the normal, despite the case that the t-distribution would have been more appropriate. But normally, we're still going to be using the normal for convenience, as we explained in terms of practical aspect. But remember that the solution will not differ by much. It's a good approach to use a normal distribution. It's not a problem. Now, the critical value, if you are dealing with large sample cases, this turns out to be x bar m minus x bar f. This doesn't change anyway. That's why I wrote it earlier. Plus or minus a normal distribution if you are dealing with large sample cases. Because if you're dealing with large sample cases, the difference here would be following a normal distribution since both samples are large, following the central limit theorem, obviously. Then you will need to multiply by the standard error. Now, the standard error means what? The standard error is the standard deviation of a statistic. If you refer to here, when we did this, we had to multiply by the standard error, which is the standard deviation of your statistic x bar. That is what gave us sigma over root n, for example, all right, as a standard error. But here, what's going to happen? If both sample sizes are large, what's going to happen? We need to know what is the standard deviation of x bar. So we will take the variance of x bar first. But here we don't have x bar. We have x bar m minus x bar f. Before I continue, I just want you not to lose focus on the idea that you are doing a comparison here. When you are dealing with the two sample cases, don't forget that the aim is to do a comparison. All right, that's what you are doing in the end. Two sample cases involve comparison at the end. In the end, sorry. Now, the variance of x bar m minus x bar f has to be found first. Then you take the square root to find the standard deviation. So what is the variance of x bar m minus x bar f? It is equal to the variance of x bar m minus x bar m plus the variance of x bar f. So this is what we know. And then you have to be careful for. Normally, that what I've just written does not make sense if what I've just written here, this formula that I've just written, does not make sense if your two samples are not independent. This formula that you see me writing down there only applies if your two samples are independent. Otherwise, it is wrong. Why? Because normally you have another term that we call the covariance. Like for example, here you would have to subtract twice the covariance of x bar m and x bar f. The covariance is a term that we discussed in when we studied correlation. But here, because we are going to assume independence, we are going to assume independence to do our confidence interval, then because of this assumption, the variance of x bar m minus x bar f becomes the variance of x bar m plus variance of x bar f. Remember that uh, when you are subtracting here, you should always add here, because remember that you are dealing with the squared values. Now, uh, then what's going to happen is that the variance of x bar m turns out to be equal to the sigma squared m over n, sigma squared m over nm plus sigma squared f over n f. So that's what it is in the end. So what is the standard deviation of x bar m minus x bar f? That is our standard error. So in other words, it becomes the square root of that part here that we just obtained. So this is how you get your confidence interval. You have to look at your question that is given to you. If your sample size are large, then what you need to do is you need to have this information, obviously, and you need to have this information sigma squared f, sigma squared m, and f. If this information are available, it becomes so straightforward because z will depend on the confidence level that you are computing. All right, if you're computing a 95% confidence interval, that z would become 1.96. If you're computing a 90, it would become 1.645. All right, this is something that we mentioned. This is what we explained to you last time, how to find these z values. So what about, we have just seen there, to be able to do that in your question, whenever you are given a question on confidence interval for two sample cases, you always have to make this assumption of independence. Like here, we need assumption of independence. Don't forget that, otherwise what you are doing is going to be wrong. Assumption of independence is essential to be able to do this to apply this confidence interval. Here what we would do is that if we are talking about claim amount, we would assume that the claim amount for male and female are independent. That's what we need to do. Then when you have done this assumption, then you would say, don't forget that all questions before you do the assumption, you have to define your first mu m, and you have to define mu f. As you need to say, let mu m be the average claim amount for male and mu f be the average claim amount for female. Then when you are done with that, you will say, before you start writing down a 95% confidence interval is computed, what you do is you would say, assuming that the claim amount for male and female are independent, then you would say, comma, a 95%, if the question is a 95%, confidence interval for mu m minus mu f is given by, then you start applying the formula as you see here directly. But remember, the assumption is very important. So that's one of the cases where you are dealing with two large sample cases. But one thing I would like to point out though, just understand something, is that very often, most of the time rather, if not all, but most of the time, what is going to happen is that these sigma squared and sigma squared f are unknown. Remember that they are parameters. If the mean is unknown, try to understand that. If the mean is unknown, generally, these will be unknown as well, most of the time. Okay. Now, if they are unknown, obviously, you won't be able to apply this formula, but you will have to apply the estimate of a sigma. If you need to apply the estimate of sigma, which is by s squared f. So in your questions, generally, you will be given information from a sample, that is the standard deviation from a sample, or the variance from a sample, that you would have to use to compute your confidence interval. So that's a bit what you need to know with regards to large sample cases. Given that generally sigma squared is unknown, you will be using s squared m and s squared f to be able to do that. Now we'll take the case of what happens if both samples are small. What happens if both samples are small? Less than 30, less than 30. If both samples are small, that is, one is less than 30, the other one is less than 30, then what would be the difference between all that we did here? So let me just try to have some order on the slide here. Our first step we go. So do not forget what we are doing is that we are estimating mu m minus mu f. The principle is the same, the point estimate plus or minus the critical value times standard errors. Given that the point estimate is the same, that's why I wrote it already here directly. So this doesn't change for the case of small samples, that is both are less than 30. Plus or minus the critical value times the standard error. Now, what is going to happen is that we have to understand that, as I said to you, most of the time, if not all, when you are trying to estimate mu m minus mu f, sigma squared m and sigma squared f will be unknown. Now, this is one thing that you need to bear in mind. They will be unknown, right? Now, given that they are unknown, and you are dealing with too small sample size, I think it should be clear what distribution has to be applied. You can do an analogy with what we did already earlier. If your sample size was small and your population variance or standard deviation was unknown, we have been applying the t distribution. So for that specific reason as well, we will be again applying a t distribution to find the critical value. Now, for the case of a one sample, the degree of freedom that was used for the t distribution was n minus 1, right? Is that you lose one data. For the case of a two sample, the degree of freedom that you are going to use would be slightly different, because now you are estimating, like here, for each parameter, that the degree of freedom is like for each parameter that you are estimating, you lose one data point. All right. Here, because you estimated only one parameter mu, you've lost one data point. But here, because you are estimating two parameters in the end, you are going to have an estimation for two parameters here, because you need x bar m and you need x bar f to estimate mu m and mu f separately. Then what is happening is that because you have an estimation over two parameters that is going on, your sample size would be represented by nm plus nf, because you have to understand that you have two samples now, it's not n. So it's going to be nm plus nf, but then not minus 1, but rather minus 2. So this is important to remember. For the case of a two-sample case, where if you are using t, the degree of freedom will turn out to be this, minus 2. Then, obviously, the next step comes to the standard error. This is where things get a little bit interesting. How? Our first assumption would be the same. We will still make an assumption that our two samples are independent. That is, for in this case, claim amount for male and female are independent. But we will bring in some additional assumptions to do this computation here. One of the assumptions, which is not something that we are bringing it as such, but is something that you already know, is that if you recall last time, to be able to use the t-distribution as the critical value, that is for the case of a small sample and sigma unknown, we have been using the t-distribution as you recall, but before you apply the confidence interval, I explained to you that you need to still make the assumption that your population is normally distributed. This was essential. You had to make an assumption that your population is normally distributed. If you do not do this assumption, then you are not supposed to be able to use t. All right, we are saying we use t, yes, but under the assumption that the population variance is under the assumption, excuse me, that the population is normally distributed. Now, the same thing applies here. If you are going to use a t-distribution for the case of two small samples, you again have to make the assumption of normality of population. Oops. Just give me a second with you. I'm trying to deal with a technical issue. Oh, I'm really sorry. There has been a small technical issue where all the information that I was writing disappeared and the PowerPoint closed. So I'll just take it again from where what I was talking about is we have here our x bar m minus x bar f, which is going to be the same, plus or minus the t distribution, where I told you that the t distribution is based on n1, nm plus nf minus 2. All right, that is what I mentioned. And then for you to be able to decide what standard error to use, you will have to base yourself on the assumption that we already discussed in before, the assumption of normality, of independence. We also need to do the assumption of normality of population. Populations, because there are two samples now, right? You assume that both populations are normally distributed. In the end, there is another concept that we call multivariate normal, but I'm not going to discuss that here. But we assume that the populations are normally distributed. But then, for why did we assume that normally distributed? Because I just told you a few seconds ago that we are going to use a t, just like when we did for mu. When we used the t distribution to estimate to obtain the critical value to estimate mu, we have been assuming the normality of populations. For the same reason that I explained that to you last week, we are going to we are going to assume that the populations are normally distributed. So in our case, it was claim amount. Okay, now we are going to assume that claim amounts for male and female come from normal populations. We assume that the claim amount for male and female come from normal populations. That's what we would have done. That is, you have to be careful when we talk about the assumption of normality. I'm not assuming that x bar m minus x bar f follows normal. This is one of the things that you have to be careful. This is why I'm mentioning population. You don't do an assumption on a sample. You do an assumption on something that is unknown. That is why I'm referring to populations here, to distinguish clearly between this and this. This is from your sample. You don't assume anything here because this is something that is observed. Here is where you do the assumption. The population is normally distributed. That is, your XM and your XF comes from normal populations. That's what we are assuming here. But we will bring in an additional assumption for this course. Now, this assumption is important for you to be able to use that degree of freedom that I'm mentioning here. I explained to you this degree of freedom earlier. To be able to apply this degree of freedom, it is based on the assumption that I'm going to state here. Otherwise, you will not be able to use that degree of freedom that I explained here if you do not make this assumption. Then you would have had to use a different degree of freedom that is based on what we call the Safford-Weight approximation. And this Safford-Weight approximation to the degree of freedom will bring in, for example, you might have a decimal place in your degree of freedom as well. It's going to be a different thing, okay? But we are relying mainly on the assumption here of, we are going to make an assumption here to make use to use this degree of freedom. And what is the assumption that we are going to make here? We are going to assume equality excuse me, I get it wrong sometimes using this, equality of population variances. Equality of population variances. So what do I mean? I'm assuming that sigma squared m equal to sigma squared f. This is an additional assumption that I bring in to be able to apply the to be able to obtain the standard error that I'm going to have here with the t based on that degree of freedom. So the assumption that I'm going to do, the last one, is the equality of population variances, also referred to as homogeneous population variances. So we assume homogeneous population variances. Now, what is going to happen when we assume that the both populations are normally distributed? Sorry, are equal, excuse me. Both population variances are equal. If you look at it well, if both population variances are equal, one of the things that you need to understand is that there is kind of no need for the subscript because we don't differ them in that sense. So it becomes just like as if we are estimating only one value. Let's take it as sigma squared, right? We take it as sigma squared. Now, just before I continue with that, I just want to recap something. What we explained for the case of large samples is that variance of x bar m was equal to the variance of x bar m plus the variance of x bar f. And this was sigma squared m over n m plus sigma squared f over n f. So this is what we just saw earlier, all right, for the large sample cases. But now we have to be careful. We also understood that we are not going to be able to use this sigma squared m over nm. So in the end, when we were working with the standard deviation of x bar m minus x bar f, we came up to the conclusion that we are going to use s squared m plus S squared F. This is what we concluded uh, before, because sigma squared is unknown. Okay. Now there is a small problem now, is that I can't use that same thing here and use that as my standard error for the case of two small samples. I can't do that. Why? Because in the end, I'm not estimating two different sigma squared. I'm estimating only one sigma squared. So if I'm estimating only one sigma squared, I will need to have only one estimate of the population variance. And that one estimate of the population variance would be based on what? It will be based on what we have as sigma squared m and sigma squared f. Now you have to understand in your questions that you will get in an exam or whatever, you have to understand that the sigma squared will be given, there will be two different sigma squared. You will not have only one sample variance. You will have two different sample variance, because when you have to understand that if you are making an assumption that sigma squared m is equal to sigma squared f, that does not mean that sigma squared m is equal to sigma squared f. That does not mean that, because you still have a possibility that your sample variance for male is different from your sample variance for female. But what we are doing is that we are assuming that they are equal in the population. In the samples may not be equal, but in the population they might be equal. So this is why you will still have two different sample variances generally. But if you have two different sample variances, you are trying to estimate only one thing. I think you would already understand that you might do an average of these two measures. We can do an average of these two measures to be able to come up with only one estimate of that sigma squared. But the only thing is that the measure that we are going to use is not going to be a simple average, but it's going to be a kind of weighted average, where we would say that sigma squared, we will call it sigma squared p. Why? The p stands for a pooled estimation that you are carrying out. That is, S squared p represent a pooled estimated sample variance. All right. The S squared p represent a pooled estimated variance for your population variance sigma squared. But that pooled estimated variance will not be just x s squared m plus s squared f divided by 2. That's not going to be the case. We are going to take into account the sample size as well. That is, we need to understand that maybe for one sample, the sample size is smaller, even smaller for the other one. Let's suppose for an m, it may be 10, for another one, and f, it may be 20, maybe twice as that of an m, things like that. So then when you are doing your estimation, you will need to take these sample size into account to be able to get a weighted average of s squared m and s squared f. So what we will do is we will be applying this formula, n m minus 1, the idea of degree of freedom, you can see it here, times s squared m plus n f minus 1 times s squared f, and the whole thing you divide by n m plus n f minus 2. All right, nm plus nf minus 2. So now look at that. Why did I tell you that it is a weighted average? You can see clearly that this is the first weight attached to s squared m, and this is the weight attached. This is the weight attached to s squared f. All right. So By the way, just for information, if you take two numbers, let's suppose I take 2 plus 4 divided by 2. This gives me 3. All right. Now, for your information, I could also rewrite this differently. I could say, okay, let me write it like this: of 2 plus half of 4. So this is going to give me 3, but it's a different way of re-expressing the same thing that you are used to. Like now the only difference in the way that I'm expressing it is that you would note that the numbers 2 are here, but then there are two weights attached to it. There is a first weight here, is a second weight here. And you will see that both weights are the same, they are equal. So in fact, that average that is common to you that you already know is itself a weighted average. It's itself a weighted average with their weights being equal. Their weight is like, for example, the importance given to a number. All right, and their weights being equal. But here it's not going to be equal because it will depend on the sample size that you have for specific cases. All right, for the first sample over second sample. But here they are equal. This concept of weighted average is used to compute inflation, but I'm going to avoid getting into all these details. You have, for example, CPI. The CPI is itself a weighted average that is computed. Just for your information, where certain items in your basket are given more importance than others. Like here, you have two numbers with the same importance, but if you look at CPI computation, you will see that not all items are going to get the same importance in the computation of the CPI. So this is why the CPI itself is a weighted average. So the concept of weighted average is not something unknown. It's something that already exists and that maybe you did not know about it, but just for information, here we are dealing with equal weights, but here they might not be equal. Okay. And so when we have come up with S squared P, that is the pole estimated variance, which is used to estimate sigma squared, it becomes so straightforward now. It becomes straightforward because sigma squared P is like estimating sigma squared M is like estimating sigma squared F. So, but the idea originally was this: sigma squared M plus sigma squared F divided by NM over NF, but we do not have separate sigma squared, we have only one sigma squared. So it becomes sigma squared P into 1 upon Nm plus 1 upon Nf. Look at the difference now. You have S squared P over Nm plus S squared P over Nf because there is only one S squared. You don't have several now. As I explained to you, we are doing this assumption here. All right. So in other words, what happened is that you have sigma squared P over Nm plus sigma squared P over Nf. So here I've just put this outside, and then just for information, you can still bring that outside as well. It becomes SP over root of SP times the root of this. That's another way of writing it. So that's how you will compute a confidence interval if you are dealing with two small samples. All right. Now, I don't need to state that we are using S squared, we are using the t not only because the small we are dealing with small sample, because we don't know sigma squared. Here it is clear that we don't know sigma squared because we are making an assumption on them. If we are making assumption on sigma squared, it means that it is unknown. So this is why we are using t, by the way, because obviously they are unknown if we are making an assumption on them. Now, if they are unknown, we are making an assumption on them, and the sample size is small, just like we explained earlier. For the one sample case, we need to use the t distribution with the appropriate degree of freedom. So that's a little bit how it is for the case of for the two sample cases. Maybe I will just now go through an example together with you. So to now, before I move on to the example, just remember that when you are going to apply that, you will get a confidence interval for the average claim amount. If you were to have a data for claim amount, for male and female, you will have an average. Now you will get an interval. Now, let me just write it on this side. You might have different type of interval. Remember that you are computing an interval estimate for the difference between mu m. Do not lose your objective. Your objective was to estimate mu m minus mu f. That was your objective originally. So what are we going to do then? We are going to get an interval estimation. There are different type of confidence interval that you can obtain. Let me just give you some examples like that. Let's suppose you are talking about claim amount in rupees, in Mauritian rupees, like you have a difference of 100 to 100. You have a difference of minus 300 minus 100. And you have a difference of minus 100 to 100. These are different possible examples that you might have. I'm just taking some fictitious numbers like that. What happens if you get an interval estimate like that when you are estimating mu m minus mu f? If you are estimating mu m minus mu f and you get a value like 100 to 100, it means obviously that what you are estimating here is that you are estimating mu m minus mu f to be a positive number because the confidence interval is positive. Both numbers are positive, so obviously it means that the confidence interval is positive. However, if you are getting a confidence interval like this, it means that when you are estimating, if you need to remember what you are starting with. If you started with mu m minus mu f and you get something like that, then it means that the confidence interval which has been estimated here is a negative confidence interval. So what does this to mean? It means that there is a significant difference between these two. Excuse me. So it means that there is significant difference if you get something like that or if you get something like that. So your first conclusion would be that there is a significant difference in the average claim amount of male and female. If that's your first conclusion. And then you can go a little bit further by saying the difference is in terms of what? Like here, we said if we get something like that, the first thing that you would say is there is a significant difference in the average claim amount of male and female. And then you would have to say, okay, because it is positive, it means that mu m minus mu f is greater than 0. So in other words, mu m is greater than mu f. So the next step would be to state the direction of the difference. So what you would say, the first thing is there is a significant difference in the average claim amount of male and female, such that male get more, male claim higher values than female, higher claim amount than female. So that is how you would interpret if you get something like this. Now, you would say that there is a significant difference in the average claim amount of male and female, such that male claim less than female, or you could say female claim more than male. It's the same thing. But what about this one? This one, you would have a negative value and you have a positive value. If you look at this clearly, you can't even state whether it is positive or you can't even state whether it is negative. But remember originally what was our aim? Our aim was to know if mu m minus mu f equal to 0 or not. So in these two cases, they are not equal to 0, so there is a significant difference. But in this case, you would observe that the value 0 is found in that interval. So if the value 0 is found in that interval, you are basically saying that there is no significant difference in the average the average claim amount of male and female. There is no significant difference in the average claim amount of male and female. So this is going to be your conclusion if you get a negative and a positive value. You are basically coming up to conclude that what you believe kind of makes sense based on data, right? But bear in mind that there is the word significant. It does not mean that it is we are taking it to be equal to 0 with 100% certainty, because there is always a level of uncertainty attached to your estimate. Right? Remember that significance, the word significance in statistics does not mean important. The word significance in statistics does not mean big. The word significance in statistics, when we refer to statistical significance, it refers to the elimination of chance effect that result from a sample, the elimination of chance effect that result from a sample. So this is why you are observing that I'm using this word significant each time. But by the way, we will get to that concept of significance a little bit more later on in the next video, where I start talking about hypothesis testing. All right, because hypothesis testing is also referred to as significance testing sometimes. So you will get a little bit more idea about the term significance there. So that's a little bit how you come up with the interpretation of these values. So let me just do a small question together with you. We have a data set here. All right, we want to try that. I'm just going to give you the element of this. I'm not going to do the computation, but just the element so that you can continue it on your own. We are saying you are investigating, you can read it, the possible differences between eighth grade boys and girls regarding their perceptions of the usefulness and relevance of science for the roles they see themselves assuming as adults. Your research hypothesis is that boys hold more positive perceptions in this regard. All right, that is a research hypothesis. But then, using an appropriate instrument, you obtain the following results, where NB is the sample size for boys, X bar B is the mean for boys perception scores, and SB is the standard deviation for boys perception score. Your question is there a significant difference in the perception scores of boys and girls? So be careful with what is stated here. Your research hypothesis is that boys hold more positive perceptions in this regard. But in the question itself, I'm not referring to that. I'm not referring to that. So if you have to answer this question, you will just try to obtain the confidence interval and see if it includes 0 or not. If it includes 0, there is no significant difference. If it does not include 0, there is a significant difference. You would have stopped there. But if you want, then you can go a little bit further to conclude whether the research hypothesis is okay or not. Okay, now, if there is a significant difference, then you can go ahead to state if the research hypothesis is appropriate or not in this context. So let's start. Our first step is, as I told you, I'm going to give you the elements of how to answer that. I'm not going to get into the details here. The first step would be to define your parameters. Let mu b and mu g be the true average perception scores of boys and girls respectively. So that's the first step. Let mu b and mu g be the true average perception scores of boys and girls respectively. Then our next step would be what? Before we start doing any computation, we need to look at the sample size. Here, the sample size are both large, okay? And you clearly see that there is no sigma is given to you. These are based on samples, all right? These are based on samples. So if no sigma is given to you, they are based on sample. We are dealing with the first case that I explained. That is large sample cases, where your confidence interval would include the normal distribution in there, and your standard error would include two different estimate of your population. It would not be the pooled estimate, that is with only one no, but it will be the two different one. If this is the case, we need to remember that there is still one assumption to do before we start writing down the confidence interval. So what is the assumption to do? The assumption to do is the assumption of independence. So what do we do? Assuming that the perception scores of boys and girls are independent. This is an assumption that we need to do. Assuming that the perception scores of boys and girls are independent, a 95%, it is not stated there, by the way, but generally you will get the confidence level, right? You will get the confidence level, but here it is not given, so we will take it as a 95% confidence interval. A 95% confidence interval for mu b minus mu g is given by. So here what we do is that we want to estimate mu b minus mu g. Why do we want to estimate mu b minus mu g? To see if it is equal to 0 or not equal to 0. If it is equal to 0, there is no significant difference. If it is not equal to 0, there is a significant difference. So this is why I'm estimating mu b minus mu g. As I repeat to you, we are using a 95 here, but in a general context, these will be given to you. The other thing that you need to understand is that the same question, I'm answering it now through confidence interval. But you have to understand that the same question could be answered through hypothesis testing, which we are going to discuss in another video. All right. So it's given by what? It's given by, we apply the formula that we have studied earlier. The formula told us that we need to take x bar 1 minus x bar 2. In the example that I took earlier, it was for claim amount, male and female, but in the general context, it's x bar 1 minus x bar 2. So how did we define it for mu b minus mu g? So is given by, if we started by mu b minus mu g, then you have to state x bar b minus x bar g is given by x bar b minus x bar g. But bear in mind something, is that when you are, if you stated mu g minus mu b, do you have to say x bar g minus x bar b? If you started with mu b minus mu g, you have to state x bar b minus x bar g. For mu g minus mu b, it's x bar g minus x bar b. But ensure that you don't reverse the position here. If this is mu b minus mu g, don't put x bar g minus mu b. Depends on how you are computing the confidence interval. Whichever way you compute it, either mu b minus mu g or mu g minus mu b, does not matter because the interpretation will be the same. If someone is computing mu b minus mu g and got something like 10, 20, the other one who would compute mu g minus mu b would get something like negative 20 and negative 10, negative 20 and negative 10. But the interpretation is the same in the end. It's just that the computation will be different, but interpretation will be the same. So x bar d minus x bar g, we don't need to write down the formula as such. We can directly state the value here and here. Plus or minus the critical value. The critical value is based on the normal distribution because both sample size are large. And if we are computing in 95, I think this should be clear that it is 1.96. I don't think we need to get into that again. Into the root of a standard, so into the root of what? The root represents the standard error here of x bar s squared b over n b plus s squared g over n g. So in other words, it is 10.2 to the squared divided by 32 plus 9.7 to the squared divided by 37. Now, be careful. There is one common mistake that many students do in exam. They forget their mathematics. Some people break down this root into 2. If you do that, it's going to be wrong. Do not, I repeat, do not think that this is the same. Do not think that this is the same. It's not the same, right? Because you have a plus there. You have to do whatever you have inside the root first, and then you take the root in the end. But don't try to break this down. You would be able to break it down if there was a multiplication here. Be careful with that. I find many students over years do these silly mistakes of mathematics. So please be very careful about that. All right. Then you are going to have your confidence interval and see what it gives you. You can compute it yourself. Don't forget, you always do the negative first, the minus first, and you put there, and you do the plus second, you put there. I'm stating that it looks like trivial, but let me tell you that again, this is another common mistake that students do in exam. Why? I don't know. But one thing that I know is that very often they do the addition first and they put that value of addition here. Like some student get, let's suppose you get 10, 20. Some student will write it 20, 10. That does not make sense. You have to start from 10 and move to 20. It's a confidence interval. How can the value be starting from 20 to 10? It has to be 10 to 20. All right. So please be careful when you're writing down your confidence interval. So I repeat, if this value is going to include 0, you would say there is no significant difference in the average perception scores of boys and girls, and you stop there. However, if it is not equal to 0, if you see that these values are not equal to 0, let's suppose you get 10, negative 10 and 20, something like this, two positive values, then you would say there is a significant difference in the perceptions of boys and girls, such that because it is positive and you did mu b minus mu g, you would say such that boys hold more positive perceptions in this regard. However, if you got something like mu b minus mu g when you did it, if you did mu b minus mu g but you got something like negative 30 and negative 10, then what would you say? There is a significant difference again. There is a significant difference in the average perception scores of boys and girls. But now, because mu b is less than mu g, you would say such that boys hold less positive perception than girl in this regard. So that's a little bit how it is. So just to complete my lecture for confidence interval, if your two samples were small, all right, if these two were small, let's suppose 10 and the other one is 20, the whole procedure would be nearly the same, but the assumption will be 3 times what you have here. So you would have 3 assumptions to do. Do not forget that. If the two samples were small, if I change this question to 2 small sample cases, the assumption will be based on, there will be 3 assumptions that you have to do. Assuming, let's suppose it was like that, we would say assuming that the perception scores of boys and girls are independent, come from normal populations, and that their population variances are equal, comma, then you write a 95% confidence interval. All right, then you continue with that. And then when you will reach here, this will stay the same, will not change, but this obviously will change to a critical value based on the t distribution, where the degree of freedom, if it was 10 and 20, would be 10 plus 20 subtract 2. So that would be your degree of freedom, okay? If you want to if you are going to use the t distribution. The other thing that would be changing is this. What you would have to do is first of all to compute your s squared p. That's the first step. to compute your S squared P through the formula that was given to you. That is here, it would be 32 minus 1 times 10.2 to the squared plus the whole thing you divide by sorry, the whole thing you would divide by these two, 10 plus 20 minus 2, which is 28. Now, just for information, if you are dealing with 28 and 28, you will come up with a situation where a your it is still small sample cases that you are dealing with. If you are dealing with 28, you are still dealing with small sample cases, but there is, when you come to your um, when you come to your degree of freedom, you have to be careful. You have to be careful. Why? Because your degree of freedom, here would be 28 plus 28 subtract 2, which is going to be 54. All right. So 56 minus 2, 54. And you may see that there might be no value of 54 in your T table. All right. But you will have to choose a value that is closer to the 54, obviously. If I'm not mistaken, there is a value of 60 there. You can use this value to get your degree of freedom. All right. So this is one of the things that you need to understand, how to compute, how to find the T. And then otherwise, everything is going to be the same in terms of interpretation as well. You will be required to do this activity where you have two small sample cases here. And this one, I'll leave it to you on self-study. And this one, you will have to do it in terms of activity. All right, it's a bit similar to this one. And that's basically all that we had to do today. So I will send you another video for hypothesis testing. Remember that when you are going to go through hypothesis testing, uh, you are required to understand the conditions that were applied for the computation of confidence interval, all right? Because these conditions are the same conditions that we are going to be to use for the hypothesis testing cases. Thank you for your attention. Bye.